The light waves from two independent sources cannot be coherent. Why is the first question. The light is actually emitted by atoms within the source. Is supposing you take a source of light. There are many atoms, and these atoms is what is emitting the light. Each atom's emission is an independent event. So each atom's emission is an independent event. Since the emission of light from different atoms is random, say for one atom may have an electron in a higher excited state, one atom may have an electron in a lower excited state, and so on. So the light falls from a higher, the electron fall from an excited state to ground state is when the light is released. So since the emission of light from different atoms is random, the phase of the waves emitted by two different sources will fluctuate also randomly and independently. Hope you're clear. So let's go to the second question. What is the phase difference between any 2 points on a wavefront? A wavefront by definition itself is the locus of the points which are vibrating in the same phase. Therefore, the phase difference will be 0. Phase difference will become 0. The third question. How does the resolving power of the telescope change in decreasing the aperture? Okay, you got to decrease the aperture. The aperture is this part. Okay, the aperture of the objective lens. Justify your answer. The resolving power of the telescope. You're going to decrease the aperture. The light gathering power will be less, and so then the sharpness of the image will also be less. How does the resolving power? So it's, according to me, it's directly proportional. The resolving power is directly proportional to the capital D, which is the aperture. So as the aperture is increased or decreased, accordingly the sharpness will also increase or decrease. The light gathering power will increase or decrease. Resolving power of a telescope change in decreasing the resolving power is directly proportional to the aperture or capital D. The formula for resolving power is R is equal to capital D, which is aperture's diameter, by 1.22 into lambda, and so then resolving power is directly proportional to aperture, as simple as that. This means it's the diameter of the primary lens or the mirror of the telescope. And you can see wavelength. From this relationship you will understand that how does it vary with the wavelength. The wavelength is larger, the resolving power will be lesser, or wavelength is lesser, the resolving power will be more. So the wavelength being observed, shorter wavelength always gives you a better resolving power. So you also understand how the resolving power and the wavelength are also related, apart from the question that's been given in the question paper. Next question is the fourth question. I hope it's getting recorded. Yes. So fourth question. Diffraction is more common in sound but not common in light waves. Why? Okay. The sound waves have a larger wavelength. Sound waves has a larger wavelength, whereas light wave has a smaller wavelength. And you know that the wavelength of the light and the aperture, or what do you call, the obstacle, has to be in comparable size to produce diffraction. That's a condition for diffraction to occur. And so then therefore there are large obstacles as big as the wavelength, and in a day-to-day life, and we get to experience diffraction in sound more common than diffraction light, because light obviously needs a smaller aperture or a smaller obstacle which is in comparable size with that of the light wave. So the next question is, define the term wavefront. You know what to define wavefront. Wavefront, or the locus of the points which are vibrating the same phase, is known as wavefront. So what is a ray of light? And this is a wave phenomenon. And this is ray optics. Ray of light is always perpendicular to the wavefront. A ray of light is always drawn perpendicular to the wavefront, and it's also progressing in the same direction as the wavefront. And this can be considered as ray optics is based on corpuscular theory. A wave is based on wave theory. So that's all you can say about these two. So the next question is the sixth question, where they have given two separate sources having intensities I and 4I. Okay, find the source intensities, like just like A and B, small a and small b. Here the intensities of the incident radiations are I and 4I. Find the intensity of where the phase difference is pi by 2 and pi. Resultant intensity, these two are actually interfering with each other, and the resultant is I1 plus I2 plus 2 root I1 I2 into cos pi is the formula, and that's for the resultant intensity. And when the angle is 90 degree, the cos 90 will become 0, and one is I, another is 4I, so the resultant intensity will be 5I. So we can call it as I resultant, it will be phi I. And what happens when it is pi? And in that case, the cos pi will become cos 180. Cos 180 is minus 1. So it will become I plus 4I minus 2 into root I1 into root I2 into cos pi is cos pi, which is minus, and I have included the minus sign here. So then therefore it is 5I, and this is another 2I, and 2 and 2 is 4 minus 4I, and so the answer is just I. So that's the resultant intensity there, and so IR becomes an I. So then let's go to next question, the seventh question. The Young's double slit experiment using light of wavelength 400 wavelength is 400 nanometer into 10 to the power minus 9 meter. The interference fringe of width x is observed. Interference fringe, okay, is x of width. We know it's lambda into capital D by small d is the fringe width, and they're saying x is observed. The wavelength of the light is increased to 600 nanometers. This is lambda 1, this is lambda 2. And the separation between the slits is halved. Which means D is becoming D by 2. If one wants the observed fringe on the screen to be the same in the two cases, the fringe width has got to be the same in both the cases. Find the ratio of the distance between the screen and the ratio of distance between the screen and these must be source, the plane of the interfering sources in the two arrangements. Okay, so then I think you got the question. Okay, so there are two wavelength. In the first case you got it at x. In the second case also it has to be x, because they are saying that the fringe width has to be same in the second case too. And so then the wavelength here is lambda 1, here the lambda 2 into what about the ratio of the distances, so you can call it as d1, in this case d2, in this case it's d by 2, and you can equate them. Lambda 1 and by this is equal to lambda 2 into d2 by d by 2, so d and d get cancelled, this goes up, the 2, and you know lambda 1 is 400 into 10 to the power minus 9 into capital D1 is equal to 2 into lambda 2, which is 600 into 10 to the power minus 9 into d2. So this and this get cancelled, the 00 and the 00 get cancelled, this and 2 get cancelled. The ratio of d1 by d2 is a 6 by 2 or a 3:1. That isn't it, d1 by d2 isn't the ratio 3:1, and that completes this question, I think. Cases. Find the ratio of the distance. Yes, that's done. That's all is the question. There's nothing more. Okay, let's go to such a simple question. The eighth question is two coherent sources where intensity ratio, the coherent source is intensity. Let's call it as I1 and I2 is in the ratio of 16:1. Produce interference fringe. Calculate the ratio of the intensity maxima and minima. Okay, so intensity I max by I minimum, I maximum by I minimum. These are basically source intensities, which you know is A by B is the amplitude, and intensity is always square of the amplitude. So this is nothing but a square by b square. Therefore, a by b is 4:1. And you know I max formula is a plus b the whole square by a minus b the whole square, which is 4 plus 1 the whole square by 4 minus 1 the whole square. So it's 25 by 9. So let's go to the next question. That's again such an easy paper. State Huygens principle with the help of suitable diagram. Prove Snell's law for refraction using Huygens principle, which you all know. I'm not doing that. It's a theory part. What is the shape of wavefront emitted by light source in the form of narrow slit? So the wavefront emitted by a narrow slit, you can see slit is like this, right? Narrow slit, not a hole. Okay, it will be obviously cylindrical wavefronts. What you will get is only a cylindrical wavefront. The wavefront emitted by a narrow slit is always cylindrical in nature. So let's go to the next question. The wavefront of the light coming from a point source placed at infinity. So obviously point source will produce only spherical wavefronts. And the next question is point source is over. Then I think wavefront of the light diverging from a point source. So then if it's going to diverge like this, then obviously it is also spherical. It is also spherical wavefronts only. So then but you can say this to be concave, spherical. No, the wavefronts is concave in nature. Can you see? So what we can call it spherical also. So let's go to next question. Is it getting recorded? Yeah. So let's go to next question. What's the next question here, Shankara? 10th question. 10th question is the shapes. It's done. 11th question. In a single slit diffraction pattern, how is the in a handwritten question paper, width of the central maxima. So in a single diffraction, how is the width of the central maxima change? How central bright maxima change when the slit width is decreased? You know the formula for central maxima is 2 into lambda into capital D by small a in a diffraction pattern. And so then the slit width is decreased. Obviously the central maxima will be more. It will be increased. The slit width is decreased. The distance between the slit and the screen is increased. When the capital D is increased, obviously the width of the central maxima will increase. Light of a smaller wavelength is used. When you use a smaller wavelength, the central maxima will also decrease. That's all. So it's all over. Such an easy paper. That's the paper on wave optics.